This is Mr. T, and this video is on Packet 3, Chapter 49, Atoms and Elements. In this handout, we're going to talk about the categories of elements in relation to the periodic table. We're then going to talk about various properties of elements, as well as what is an element. We'll do it from a historical perspective. We'll start off with the very earliest models to the later ones. And then we'll start getting into other aspects of chemistry, such as nuclear symbols. So let's go ahead and begin. Now, the periodic table is designed so that it groups together elements with repeating properties. Here's a periodic table that you're allowed to use on quizzes and exams. You'll notice there's a number at the very top, atomic number 1, 2, 3, 4. And as you increase an atomic number, we find that the element properties also repeat, hence the term periodic. So we go from 1, we go to 2, we go to 3, and it turns out in group 1, they all share similar ions, such as positive ions. Again, you do not need to know what that term positive ion means, just know that they have similar properties. Consequently, they have something called common group names. This first one to the very left, starting at lithium, sodium, potassium, that goes by the name alkali metals because they all share properties of metal, and they also create very potent bases. And another word for base is alkali. At this point, I need you to go ahead and memorize these common group names. There's alkali metals, alkaline earths, transition elements, halogens, and noble gases. Now, we have an umbrella term which refers to group 1 and 2, or 1A, 2A, and then 3A to 8A. And that umbrella group name is representative elements. So going back to our periodic table, fluorine, it's in group 7A, and that's a halogen. It also is in the umbrella group for representative elements. So it has two group names. Oxygen only has the group name representative elements. Neon has two group names. It has noble gases and representative elements. And then iron is considered a transition element, also known as transition metal. So be sure to identify the common group names based on the location. You'll notice at the very bottom that I'm highlighting, those are called inner transition metals. We don't focus on those for this introductory class, so it's not even in the this slide that you need to study. So memorize all categories of elements, be able to identify on a periodic table. Now my next comment is on the difference between 1A and 1. So we have two ways of numbering the groups. We can number 1, 2, 3, 4, 5, all the way up to 18. Or we can number it 1A, 2A, and then we skip the transition elements and go straight to 3A. You'll notice for representative elements, um, it actually has 2 ways of grouping it. Whereas for transition elements, we really need to go by 3 and 4. So this is represented inside the periodic table. So it's 1A, 2A, and then it jumps over to 3A. Now, in short, we have 2 ways of naming it. The A's represent the representative elements, and that's where we will spend the bulk of our chemistry time. And that's because the rules for the representative elements are very, very easy. The transition elements, they're not listed in that Roman numeral A category. Why? Because transition elements, all of their properties are really in transition. Quiz and exam wise, the rules for them are extremely complicated. So it'll be my goal to try to shield you from a lot of the transition element properties just because there are so many various properties. They're in transition. So be familiar with both of the numbering schemes. Now, looking at your periodic table, you'll notice that there are, and I'll go and I'll highlight it right here. There are specific elements that are highlighted. Oops, let me use my highlighter. So boron, silicon, boron, silicon, germanium, arsenic, antimony, telium, polonium, astatine, not iodine. Oh well. So these are what we call metalloids, and they are the barrier between nonmetals, which are on the right side, and metals, which are on the left side. So you need to memorize the metalloids. And you need to be able to identify one. So for example, I could say, you can't see it here, but there's a carbon. There's carbon, there's nitrogen, there's oxygen. You would have to memorize that these are non-metals. Whereas over on the other side, there might be sodium, and then that's considered a metal. So you want to practice memorizing that imaginary border between the metals and non-metals, and make sure to have these elements, metalloid elements, memorized. Know the properties, which are actually pretty easy. Metals are shiny and ductile, just like wire, for example. Ductile means they can be pulled into wires. They're good conductors of heat and electricity. Nonmetals are the exact opposite, dull, brittle, and good insulators. So charcoal cannot conduct electricity, for example, and it's very brittle. And metalloids are somewhere in between. So silicon is a very popular metalloid, as it has properties of both of them. So we call them semiconductors. They're not quite conductors, they're not quite insulators. So make sure you have the properties memorized, and you have the metalloids memorized, and then you could reason out the other elements, whether they're metals or nonmetals. So that's pretty straightforward. Now we're going to start getting into Dalton's atomic theory. So this is from a historical perspective, vantage point. So he determined that all substances, he reasoned out that all substances are made up of tiny particles that he called atoms. And I believe he discovered this by playing a game where he had to, excuse me, he discovered it by doing research in gases, and then reasoned out that all gas particles were made up of fundamental atom building blocks. There was another great researcher by the name of Democritus who actually came up with the concept of atom, but Dalton was the one who really got the scientific community to embrace it. Now we're going to go ahead and go into the Rutherford model of what an atom is. Atoms are made up of protons, electrons, and neutrons. We have the nucleus, which is right in the center, which is what I'm circling, and then we have a protons and neutrons embedded in the nucleus, and then we have a surrounding electron cloud. Again, these are all models, again, simplified copy. So we have different types of models. So the bottom one is an electron cloud model, because what we've discovered is electrons aren't stationary but like to move around very quickly. So we've labeled protons, neutrons, and electrons. Make sure you're familiar with those. And then let's assume that electrons are always going to have a negative charge. Protons will always have a positive charge. And neutrons are always going to be neutral. Hence the term neutral. That's pretty straightforward. Now, one of the key fabrics of the universe is electrostatic cohesion. In other words, opposite charges attract. So opposite charges attract, which is what you see right here. So the whole reason that the electron doesn't fly off into oblivion, but stays near the center of the nucleus is because of opposite charge attraction. Now it turns out if you get two like charges, they do repel. So in the center, we've got a whole bunch of subatomic particles called neutrons, which are neutral. So the neutral ones, you don't have to worry about repelling. We also have other types of weird particles called gluons that we're not going to get into, which help keep like positive charges, such as like protons, close together. That's a whole other ball of wax, and you're not going to be tested on that kind of stuff. So make sure you're familiar with the Rutherford model. On a side note, there was another type of competing model called the Thomas model, or the plum pudding model, because it looked like plum pudding with raisins inside the pudding, where they thought the electrons were all equally spread out and the protons were equally spread out, not in a nucleus. The Rutherford model, however, had some nice, unique research which justified that there's a tight core, or nucleus core, that contains the protons and neutrons. And what he did was he had a gold foil that he went ahead and placed.
And screen to glow.
I'll go ahead and erase that. A gold foil where he would shoot it with these special nuclear particles. You don't have to worry about what those are. Beta particles, but we're not going to get into that. And he surrounded the gold foil with a special detector. And he reasoned out that if you have a tight, very tight, dense nucleus, then these special radioactive particles will actually bounce off of it. And what you'll notice is that that's exactly what happens. the gold foil's nuclei basically deflected these incoming radioactive beta particles. And it resulted in all these off-angle um, uh, detected radioactive particles on the detector. So there's the nucleus of the gold atoms, and they're being deflected. And it's by this simple experiment that the Rutherford model was justified. So you can answer these questions right here. And now we're going to relate the Rutherford model with the periodic table. Sketching a crude model of an atom. I have the nucleus. Inside this nucleus, there are 11 positively charged neutrons, and there's a mixture of 11 positively charged protons. So that's a tongue twister. 11 positively charged protons, and then a mixture of neutrons, and that can vary. Can be 11 to 13. And then surrounding it is the electron cloud containing electrons. And it turns out for neutral sodium, we're going to have a surrounding 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now this is a crude Rutherford model, but in short, we needed to summarize this information on the periodic table. So accessing your periodic table, you'll notice that there's a number on top of the element. That's called the atomic number. That tells us how many protons and how many electrons are in a neutral element. Now, if we have an excess amount of protons compared to electrons, then it's going to have an excess positive charge. If we have an excess amount of electrons, then it's an excess amount of negative charge. So we always want to make sure that for a neutral atom, the number of positives equal the number of negatives. That's what makes nature happy. So ergo, the periodic table is set up to describe neutral elements. And so it can be inferred that the 11 is for both 11 positive protons and 11 negative electrons. So you should automatically figure out the number of protons, electrons based on the atomic number. So for example, oxygen, it's got an atomic number of 8, so it's got 8 protons and 8 electrons. Unfortunately, based on the periodic table of elements, you cannot immediately figure out whether each atom has a specific number of neutrons. Some oxygen atoms within the element will have, for example, 8 neutrons. Other ones will have 9 neutrons. It will actually vary. But you can absolutely know based on the periodic table the number of protons and electrons based on the atomic number. So here are various examples for you to practice with. Make sure to know that concept. Also, be sure to understand the idea that for a neutral stable atom, the number of protons will always equal the number of electrons. Hence, aluminum has an atomic number of 13. So 13 protons, 13 electrons. Overall, it equals 0. Net charge is 0, so it's stable. Now, we're going to get into something called the mass number. And we're going to get into something called nuclear symbols. So the mass number is made so that it references the number of neutrons. There is no mass number in the periodic table of elements. A lot of people think that the number below the element is the mass number, and it is not. That's something a little bit different. We'll get into that a little bit later. You actually need special nuclear a nuclear periodic table in order to easily figure out how many or figure out what the mass number is. So let's go ahead and first define mass number. Mass number is the sum of the protons and neutrons. So mass number equals the protons and the neutrons. So you have to add those together, and that equals the mass number. So for example, if I have an element that has 2 protons and 2 neutrons, it's going to have a mass number of 4. A mass number of 4. If I were to sit there and have a mass number of 8, and I know that there's going to be 4 protons, then I can use my simple algebra to figure out the number of neutrons. So a mass number of 8, 4 protons plus x, and that's going to be x equals 4 neutrons. So oftentimes what we'd like to do to students is give them the mass number and then have them use their algebra to figure out what the number of neutrons is. So here is hydrogen. There's the mass number, and we may not just flat out tell you what the number of protons, for example, is. Maybe they will give you the atomic number. For example, for hydrogen, if I have a mass number of 1 and I have an atomic number of 1, we know that mass number is the total of protons and neutrons. The atomic number of 1 means that there's 1 proton, 1 proton, 1 electrons. Now in this instance, electrons are not relevant, so we're just going to focus on the proton. And so therefore 1 equals 1 plus n. The number of neutrons is going to be 0. Another very quick way of doing this is to go ahead and say mass number minus atomic number is equal to whatever that is. So it wouldn't be 0 actually. So let's say for hydrogen, the mass number was 1, atomic number was 1, so therefore it's going to be 0. Let's say I had something like carbon. Let's say I had a mass number of 12. I have an atomic number of 6. And then I have 6 neutrons. Let's say I have something like helium. I have a mass number of 3. I have an atomic number of 2. And so it's going to give me 1 neutron. Or let's do hydrogen again, and maybe hydrogen has a different mass number. And maybe we'll say it has a 2. And then the atomic number is still going to be 1. And then it's going to be 1 neutron. So a couple things. Atomic numbers, they never change for an element. So carbon will always have an atomic number of 6. Matter of fact, it's the number of protons that determines the element. So hydrogen, you know you're dealing with hydrogen if you have a nucleus where it only has 1 proton always. On the other hand, if I were to sit there and add 5 protons to the 1 proton of a hydrogen with a total of 6 protons, then I actually create a brand new element, which is carbon. And this is actually the building blocks of nuclear chemistry, where we can actually create new elements from old ones by adding or deleting the number of protons. Nature does this all the time naturally. Radioactivity is nothing more than exploding nuclei. And when the nuclei explodes or breaks apart, it cuts into fragments the number of protons, and then you change elements. So radioactive uranium, over a long period of time, the nuclei will decay and form lead. Now, alchemy was obsessed with adding protons in order to create gold, and it turns out scientists can now create gold, believe it or not. Unfortunately, it costs more to create the gold than it does to mine it. I digress. Mass numbers, however, can change. So, the number of neutrons per atom can vary. It can always vary. So, for example, you can have a hydrogen which has a mass number of 1, or hydrogen with a mass number of 2. Now keep in mind, neutrons are neutral. So having more neutrons doesn't affect the stability of the element. Now, we need a more efficient way of letting people know the mass number and atomic number. And so this is where we get into something called nuclear symbols. So here is the nuclear symbol for hydrogen. And again, this is different from the periodic table of element symbols. Those chemical symbols are completely different from nuclear symbols. So in this nuclear symbol, if I wanted to describe the mass number and atomic number for hydrogen, then I would write it in this format, where the mass number is written in the upper left-hand corner, and then the atomic number is written down below. So that right there is the nuclear symbol for this hydrogen. I can do the same thing with carbon. And I can do the same thing with helium. And I can do the same thing with the other hydrogen. Part of the reason they do that is to make the math really easy. Automatically, by aligning this up the way it is, you simply take the top mass number minus the bottom atomic number, and automatically that tells you the number of neutrons. So for this nuclear symbol, the number of neutrons for this carbon is going to be 6 neutrons. Now, because neutrons tend to be neutral, in chemistry land we don't really care about them as much. Nuclear chemists or physicists, or any type of nuclear physicist, neutrons are very important for nuclear reactions. Those are ones where you build up or you break down the nucleus of elements. And then neutrons become very important. But for chemistry, we try to ignore them and push them to the side, and there's different techniques we do in order to do that. Neutrons do have mass, though. So by having more neutrons, then the more heavier the elements are. And protons also have mass, whereas electrons do not. And I'll get into that in just a second. But now I want to introduce another topic really quick, and I'll use my black pen. Isotope. Isotopes is an element with the same number of neutrons. So it's an element with the same number of neutrons. So let's go ahead and take a look at these two nuclear symbols. So this right here is a nuclear symbol for one isotope, because that means all of the hydrogen atoms in that one isotope, they all have one proton and one neutron in their nucleus. Now, of course, they're surrounded by electrons, but we're not focusing on electrons, we're only focusing on the nuclei. So it has nothing to do with whether there's more or less electrons there. It's all about the nuclei. So that's one isotope. Let's take a look at the next one down below. And hydrogen, when it has, oops, and I made a mistake. Oh no, I didn't do my simple subtraction. 1 minus 1 is 0, so this isotope, all of the atoms in the isotope should have 0 neutrons. Ooh, that was ugly. My bad. Let's do the next one. So in this case, 2 minus 1, that's going to be 1 neutron. So 1 proton, 1 neutron. 1 proton, 1 neutron. So notice they're the same element with the same number of neutrons. Another definition of isotope is that they have the same atomic number. And if they have the same atomic number, then they're obviously the same element. And they have the same mass number. So therefore, they have the same number of neutrons. Now, let's go ahead and move on. So here are some nice models showing the nuclei, protons, electrons, and then the neutrons. And again, this is from a periodic table of elements right here. There is no mass number on there, so there's no way to infer how many neutrons are present. So we'll go through those examples. Here are definitions for my isotope. Now please keep in mind, so if you have one isotope, they're the same element with the same mass number. If I were to have 3 isotopes, then they'd all have different mass numbers because they all have different numbers of neutrons. So if you look to the right, over here we have 3 nuclear symbols, and then the one on the left has a mass number of 24, then 25, 26. So therefore, they all have different numbers of neutrons, and therefore there's 3 different isotopes. Now here's a frustrating thing that chemists don't like. It's very rare to have a substance that is a pure isotope. We have to use special centrifuges in order to artificially induce it. But naturally in nature, it's a mixture of different isotopes. Now let's get into weight. One proton has a weight measurement of 1 atomic mass unit. So just as you have pounds and grams, we have a weight scale um, for the subatomic particles. So a proton, 1 atomic mass unit, 1 neutron, 1 atomic mass unit. And then if I have 1 electron, for all references, it's a 0. So only realistically and in practicality, you have to worry about protons and neutrons when it comes to weight. So, for example, if I were to sit there and look at the periodic table, here's my chemical symbol for carbon, and it should say something like this, 12.01. And that number right there is the weight of protons and neutrons, but not electrons. Now there's more to that number than just protons and neutrons. It's actually a weighted average, and we'll get into that in a second. Now, because electrons are such a lightweight, they're 2,000 times lighter than a proton or neutron, then they're really, really fast. So, just to give you an example, this right here is hydrogen. This is 1 proton. It also goes by a common name called deuterium. And the other name for this is heavy water, because we tend to see deuterium in nuclear power plants. But I digress. And then here is the electron. And because the electron is so fast, it'll sit there and fly around super quick relative to the very heavy, slow-prodding nucleus, protons and electrons, and they just kind of stay in the center because the electrons are so fast. Because the electrons is super fast, then that's where we get the term electron cloud, because after a while it looks kind of like a blur. But to make everything nice and pretty and reasonable, we tend to just draw a single circle representing the electron. And we pretend like it's an orbit, when in reality it's like a green fly that just zooms around super quick. To demonstrate, what you're looking at is that the purple or the blue thing in the center. That's a tight nucleus, and then there's some space in between, and then that cloud is actually a single electron moving so fast that it looks like a blur or a cloud. So that's a single electron moving around super quick. Ergo, the term electron cloud. But my point is this: because electrons are so much lighter than protons and neutrons, it's able to fly around at a really fast rate. So let's go ahead and move on. We just talked about nuclear symbols. Slide 23 talks about it, gives you examples. You should be able to go from given data of protons, neutrons, and electrons to sketching a nuclear symbol. And then vice versa, if given a nuclear symbol, you should be able to sketch or write down the number of protons, neutrons, and electrons. Keep in mind, for all nuclear symbols, we assume that they're always, always, always going to be neutral. And if they're neutral, then that means the number of protons will always equal the number of electrons. So for example, for carbon 12, this is going to have 6 protons, 6 electrons, and then do the 12 minus 6, that's 6 neutrons. So these are 3 different isotopes because they have a different number of neutrons. But notice they have the same number of protons, and because it's neutral, the same number of electrons. After a while, nuclear physicists get lazy, so oftentimes you'll see a nuclear symbol written like this, because you can reason out what the atomic number is if you know what the element is. They also go by a written name, carbon 12. So it just looks like an element name from an element symbol, only they also include the number afterwards. So that's another way of writing a nuclear symbol. So be familiar with that. So more examples for you to work through and reasoning. And now we're going to get back to this slide right here. Now I just made a big deal that protons and neutrons, not only do they have weight, but because the neutrons are neutral, then nature doesn't care if substances are a mixture of isotopes. So for example, pure substance magnesium is a mixture of these three popular isotopes. And there's other trace isotopes that can also occur. And scientists have gotten really clever, and they figured out the abundance of each individual type of isotope present in the pure substance magnesium found on Earth. So they found, and we're not going to get into the research of how they figured that out, but they found, for example, magnesium-24. It is a pretty popular isotope with 78.9% of all magnesium on Earth being magnesium-24 isotope. And then 10% for magnesium-25, 11% for magnesium-26. So every single piece of magnesium is a mixture of it, from an 80-10-10 mixture. Now, because neutrons are neutral, we don't care about the neutrons when we do our chemical reactions. However, the more neutrons you have, the heavier then that particular isotope is. So if you have a mixture of different weighing isotopes, then chemists don't like that, because when we put something on a mass balance, then that may throw off the weight. So here's another example of this various isotopes broken down by abundance. And again, if I were to sit there and change the percentage of a particular isotope, because they all weigh differently, then I change the overall weight of the substance. So, scientists wanted to figure out a clever way of not having to worry about isotopes and weight, because we do a lot of weight measurements, figuring out the mass whenever we do our chemical experiments. So what we decided to do as a chemical body all over the planet, we decided to go ahead and find the average isotopic mass weight. So if we go ahead and you go back to magnesium, what they did was they found the average weight. So for magnesium-24, magnesium-25, magnesium-26, if you take a look at your periodic table and you find magnesium, the average atomic weight for all of those isotopes is going to be 24.305. Now, the weight for the averages was determined by instruments, and every instrument, based on how much money you spend for it, will have a specific amount of significant figures that we've already talked about. So the big pharmaceutical companies, they have the more expensive instruments, and so they'll have a lot more sig figs in their answers. Whereas the community college budget periodic tables, they tend to have a smaller one. So every periodic table will have slightly different numbers. So what do you need to do now? First thing I want you to do is I want you to memorize this definition. The purpose of, and I didn't say it before, so I need to say it right now. This average atomic weight we call an atomic mass. Atomic mass. Okay, so that's the atomic mass. So the purpose of the atomic mass is it's a measured, because it's taken from instruments, weighted average. Because remember, they figured out the percentages of each of the isotopes. So it's a weighted average, allowing us to ignore variations in isotopic masses. So this is a popular exam question that I love asking students. What is the purpose of atomic mass? So make sure you have that definition memorized. But by generating all of these atomic masses for each of the elements in the periodic table, we're able to discard worrying about isotopic weights, and it makes our math so much easier. So now you are going to need to calculate the atomic mass if I give you the starting isotopic mass data that you see here. So for example, in the box for copper, I give you the atomic mass unit 62.930 for copper 63 and 64.928 for copper 65. I then give you the abundance for each of these, and you're going to have to calculate the weighted average. So this is what we do. First thing we need to do is we need to turn these into decimal. So I divide this by 100, divide this by 100, and it gives me 0.6909 and 0.3091. I then need to multiply each one of these individually to come up with an intermediate answer. Here are the intermediate values. Please note all of these are measured values. So as you're doing your calculation, the starting value has 5 sig figs for 62.930, and the decimal form has 4 sig figs. Same thing with the other one, 5 sig figs, 4 sig figs. So just as we had to do our ugly math calculations for the chapter 1-2 portion, we had to figure out your final answer with appropriate sig figs. You got to do the same thing here. So our intermediate answers, you have to account for least sig figs because it's multiplication. So here is my intermediate value here, 43.48. And then 20.07. You then go ahead and add it together. And you have to go by least decimal places when you add it together. And then your final answer is going to be 63.55. Now, again, this data is generated from instruments. And so if you have different instruments with different sig figs, you'll have slightly different numbers. So every periodic table from a different company has very slightly different values in their atomic mass units. For example, this company has a lot of money, and so their instruments have a lot of accuracy, so high significant figures, and therefore it's more accurate than the one that I just showed you. That was from my community college budget. So this is 63.546. So this is why it's important that I indicate to you which periodic table you need to use for each quiz and exam, which should be this one that's taken from the Canvas website. So be sure to practice how to calculate the atomic mass. You'll get an example just like this on a future quiz or exam. And let's move forward. So now we've talked about where the atomic masses come from, and this is what we like to use because they make our life a lot easier. Now, when I ask you to come up with an atomic mass on a quiz or exam, rather than you just cheating and looking at the periodic table, although technically it's not cheating because you have it in front of you, I'll probably make up an element. So that way you just can't look at the periodic table. So make sure you understand the process. So far, we've talked about categories. We talked about the history of the atom and the makeup of the atom, the subatomic particles, protons, neutrons, electrons, mass number. We talked about atomic number. Then we started getting into neutrons and started talking about nuclear symbols and isotopes. And then we talked about bypassing the whole issue with having different isotopes resulting in different weights. Finally, we talked about atomic mass, and that's the weighted average of isotopic masses in order to discard the different types of isotopes in our calculations. Now we're going to get into electrons and how they're configured around the nucleus. So we've already talked about the Rutherford model. Now we're going to talk about two sister models called the Bohr model and the Heisenberg model. Now in chemistry land, we really care about the electrons, unlike in physics land. So we need to understand how the electrons are organized around the nucleus, or configured, or arranged, or whatever word you want to use, in order to predict chemical reactions, which will be important later on. Let's go ahead and go into detail on this. On the left side, we see the Bohr model. It looks very similar to the Rutherford model, only there's many layers where each layer contains a certain number of electrons. Oftentimes, we nickname this the planetary model because the electrons in this model simply orbit around the nucleus, like planets around the sun. We're going to be heavily investing in the Bohr model so that we can apply it in future chemistry concepts. The more advanced model is called the Heisenberg model, also known as the flying food model, because the electrons, they don't like to travel in orbits like in the Bohr model. They like to move around like a zipping fly around a piece of food. And we'll get into that in a bit. So let's jump right into the Bohr model. To explain the Bohr model, let's go ahead and talk about housing. So this right here is an apartment complex. Here we have different levels within an apartment complex. Now, inside a housing complex, each floor may have a different arrangement for living. So on the first floor, imagine this would be a studio apartment, and it can comfortably fit 2 people in there. In the second floor, however, the second floor might be able to fit up to 8 people. So the maximum occupancy would be 8. Now it could fit less than that, But once you have 8 people in there, then new tenants need to go to the 3rd floor, and then the process repeats itself. Now, such a apartment complex might be organized by how in shape people are. So, if I were to sit there and have a stairway that goes all the way to the top, that's my ugly stairway, the most fit people would probably be on the very top because they'd be able to go up the stairs. The people on the very bottom may not be as fit. So I'll just say not as fit. So the more fit you are, the more energy you have, then the higher that you can live. So using that as a using that housing analogy or apartment complex analogy, let's go ahead and show you the organization for the Bohr model. The first level, also known as the first energy level, we can have up to 2 electrons. The second floor, or what's known as the second energy level, these electrons have more energy. So they have twice the energy as the first energy level. And you can have up to 8 electrons put in. Now electrons like to stay away from each other. So if you have less than 8, then they will space out at a 90-degree angle. After 4, then they have no choice but to pair up. At which point, when you've achieved 8, then you have to go to the next energy level. And then the really in shape electrons, the one with the highest energy, like to go ahead and populate the 3rd energy level. And it can hold up to 8 electrons. Until we get to the next energy level. Now you'll notice a pattern here. In the first energy level, the maximum occupancy is 2 electrons. So we call that the duet rule because it only fits 2. On the other hand, in the second energy level, you can hold up to 8 electrons. So we call that the octet rule. Although you can have less than 8, you can't exceed the 8 electrons, or the octet rule. So you'll notice this is how the electrons are arranged. So each energy level can hold up to 2 electrons at the first energy level, and then more electrons for each individual level. So if we go back to slide 38, this is the Bohr model for sodium. Sodium has it has an atomic number of 11, so therefore it has 11 protons and 11 electrons. There's the protons in the center. And then when we go ahead and populate the electrons, we start from the innermost energy level and work our way out. So I'll just kind of go ahead and number it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice the second energy level can hold a maximum of 8, so then we have to go to the next energy level, and then there's the 11th one. You're going to be expected to sketch a Bohr model given a specific element. So this is pretty easy to do. Let's go ahead and take a look at the pattern. First thing we need to do is to have a periodic table. You don't have to memorize the atomic numbers, but let's just go ahead and pick one. So example, we'll go ahead and we'll pick carbon. Carbon has an atomic number of 6. That means there are 6 protons and 6 electrons. And then I'm going to, since we're already here, I'm just going to go ahead. If I'm going to pick on carbon, I'll do oxygen, and then I'll go ahead and I'll do calcium. So carbon has 6, oxygen has 8, calcium has 20. So let's go ahead and make the Bohr models for those. There's carbon. It has an atomic number of 6. Oxygen has 8. And calcium has an atomic number of 20. So the first thing we do is we draw the nucleus. We draw our first energy level, n equals 1. And we go ahead and we put in 2 electrons. And in the first energy level, they can be close to each other. We then go ahead and draw another energy level, n equals 2. So what I do is I'll just draw the electrons right here. 1, 2, 3, 4, 5, 6. So there was 2 on the first one. Let's go ahead and populate this one. 1, 2, 3, 4. 1, 2, 3, 4. And voila. There is our Bohr model. Let's go to oxygen. There's my nucleus. First energy level, n equals 1. 1 and 2. I'm going to put in my electrons. 1, 2, 3, 4, 5, 6, 7, 8. So you just got rid of the first 2 electrons. I'll then put in the next one. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Uh-oh. I put too many in there. It's just going to be 5 and 6. There we go. So we have, in the second energy level, we have 2 electron pairs, and then we have 2 single, or what we call, well, we'll just call them individual electrons at this point. Now let's do calcium. Let's get a lot of big space here. There's my nucleus for n equals 1, 2 electrons. Here is the second energy level. Now you can go ahead and write out all the electrons and then scratch them out, or you can just start to count like I'm doing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 electrons, started with 20, so there's 10 left. 1, 2, 3, 4, 5, 6, 7, 8. So there's 2 electrons left. So I now have to go to the next energy level. Keep in mind, for all the energy levels after 1, there should only be a maximum of 8. Then you have to go to the next energy level. And then there's 1 and 2. And voila, there's our Bohr model for calcium. So I could test you up to calcium for predicting the Bohr model from the starting element symbol given the atomic number from the periodic table. Now, there's something on the next page called electron arrangement, EA for short. And this is pretty straightforward. On the first energy level, we had 2 electrons. So for carbon, you'd write 2. When you go to the next, or you transition to the next energy level, we'll just put a comma there. And on the next energy level, we have 4 electrons. 1, 2, 3, 4. So the electron arrangement for carbon is going to be 2, 4. So electron arrangement is a notation method which summarizes the number of electrons per energy level for a Bohr model. So let's do oxygen. 1, 2 on the first energy level, and then 6 on the second one. And then calcium is going to be 2, 8, 8, 2. So those are the 3 electron arrangements. Be sure you're able to do those. So this slide talks a little bit about that. Other concepts that are important. There's my nucleus. I'm going to do lithium. So first energy level, n equals 1. Second energy level, n equals 2. And there's one leftover electron because the atomic number of lithium is 3. That's a really ugly nucleus, I'm sorry. But my point is this. The outermost electron is what we call a valence electrons. So in n equals 2, those are the outermost electrons. There's only one of them, but these are valence electrons. The inner electrons, these are called the core electrons. The core electrons. So let's go ahead and do sodium again. Sodium atomic number of 11. So it's got 11 protons and 11 electrons. So 1 and 2 for n equals 1. N equals 2. 1, 2, 3, 4. Make sure to put them in clockwise like I'm doing it, so that way you know the proper number of paired versus unpaired. And then n equals 3. There's going to be 1 electron. The total number of valence electrons in this instance is going to be 1 valence electron. And then the total number of core electrons, so core is going to equal 10 electrons. So make sure you know those terms. Now it turns out it's the valence electrons that actually like to participate in chemical reactions, the whole bonding, breaking, and bond making process that we talked about at the beginning of the first packet. Also, you'll notice a pattern here. For group 2, or 2A, whichever number group you want to use, the valence electron is always 2 electrons. 2 electrons, 2 electrons, and 2 electrons. So if you ever need to figure out the total number of valence electrons, just look at the group number. So phosphorus is in group 5, so therefore it has 5 valence electrons. Potassium is in group 1, or 1A, and therefore it has 1 valence electrons. So that's important. Now we're going to get into Heisenberg's fly on food model. So to understand Heisenberg model, first thing we need to do is go ahead and draw my nucleus. And I'm going to go ahead and use a piece of turkey. There's my turkey right there. And then I'm going to go ahead and draw an electron. And I'm going to use an analogy where there's a piece of, or there's a fly that's hovering around a piece of turkey outside. Now, flies, even though you shoo them away, they're not going to sit there and orbit around a piece of turkey, for example. What they're going to do is they're going to come in and go away. They're going to come in and go away. They'll go ahead and they'll buzz right by, do a flyby. They'll come closer, they'll double back on themselves, and then they'll fly away. So you notice the erratic pattern of the fly? Well, the same thing occurs with electrons. This is the more realistic atomic model that we have. The electron in the first energy level, we'll just call this n equals 1. Instead of orbiting, it'll sit there and come close to the nucleus, and then it'll fly away. It'll double back, it'll zigzag around, It'll fly around. It'll switch back. So this is a semi-erratic pattern for the electron. More importantly, the electrons you can't track. The electrons are moving so fast, we're literally uncertain of where the electron is. Matter of fact, there was a scientist by the name of Heisenberg who came up with this process and figured out that you cannot figure out where the electron is, so we called it the Heisenberg uncertainty principle, because we don't know where they're at. What we can do is make best guesses of where they're at. So just as the fly is going to stay pretty close to the turkey dinner, we could sit there and put a imaginary circle or sphere around the area that we're most likely to find the fly. And we'll say that there's a high probability we'll find the fly next to the piece of food. And then outside the sphere, we'll say that there is a low probability. We do the exact same thing with electrons. We call these shells that surround the electron, we call these orbitals. And they're a region of space where there's a high probability of finding an electron. So that's the best we can do in this bad situation of trying to narrow down the electron, because we're uncertain where it's at. So we just kind of figure out the localized region. So the definition of an orbital is it's a region of space where there's a high probability of finding an electron. So in this picture right here, it shows the erratic pattern of the electron. Now, we can't use our instruments to figure out where it's currently at, but what we can do is we can use a combination of instruments and math to figure out where it's been. So what you're looking at to the right are electron footprints. So every one of those little orange dots is a footprint of where the electron has been. So pretend that the electron was jumping around like it's a flea, and every time it jumps around, it leaves a footprint of where it's been. So here it was here, then it was here, then it was here, then it was here. These footprints allow us to come up with a nice orbital shell to enclose the space of where there's a high probability of finding the electron. Now, different orbitals have different flight paths. Consequently, they leave different footprints and they have different orbital shell shapes. So for the hydrogen atom, where it has one single electron, that electron is found in a spherical, it's found in a spherical shaped shell. Say that 10 times. A spherical shaped shell. So we call this an s orbital. Now they didn't get the letter s from spherical, but just run with it. That's a good little mnemonic trick. So think s orbital, spherical shell. Now, there's other electrons that have a little bit more energy, and we talked about how electrons, they live at higher energy levels if they have more energy. Well, these other electrons have so much energy that their footprints indicate that it has this peanut shape. So here are the footprints of these higher energy level electrons, and it's a peanut shape. So the name of this orbital is a p orbital. Again, the letter is not for peanut, but it's a good mnemonic trick. So there's the p orbital. So let's go back to this picture right here. Instead of having electrons go in orbits, each pair of electrons is going to occupy a specific orbital. And the orbital will have a specific shape. It could have an s orbital shape. So here we have s orbital shape electrons. Or it could have a, and I'll use my black pen, or it could have a p orbital shape. Going back to my housing anatomy, we talked about the anatomy of an apartment complex has levels. Well, in the Heisenberg model, not only is there levels, there's also rooms. So in the first level, you can think of it as a studio, and that would be like a that would be what we call a 1s orbital. In the second energy level, then you're going to have an s orbital. So second energy level is going to be s, and then you'll also have another room for the p orbitals. So in the second energy level, you can have up to 3 of the p orbitals. So think of the orbitals as like rooms. Call this px, py, and pz. So all of the 11 electrons occupy different orbitals. And to make things really confusing is that the electrons can pass through the region of space that other orbitals occupy. So here we've labeled the orbitals, p orbitals, s orbitals. Now the bigger the atom, the more electrons, and then the more unique configuration of orbitals are found in that atom. So here we have s orbital, p orbital, and then when you go further down the periodic table, down the rows, it's d, and then there's f. Now, drawing something like this on an exam is a nightmare. So, there's the p orbital examples. So we have something called electron configuration. So just like electron arrangement, so for carbon it was 2, 4. The configuration gives the energy level and gives the orbital type that's present per that energy level. So on the first energy level, I said that there's an s orbital, so it's 1s. On the second energy level, I said that there's an s, and there's 3 p orbitals, so there's the p's. And then in the superscript, the numbers on top, those are the number of electrons that occupy. So in this case, there's only one of the s orbitals, so it can occupy up to 2 electrons. The second energy level, each s orbital can occupy 2 electrons. There's only one of the s orbitals. There's 3 of the p orbitals. Now don't get the term 2 confused, and don't get the term 2 energy level confused with the number of orbitals. There's actually a px orbital, a py orbital, and a pz orbital. So that's what I mean by 3 of the p orbitals. And each one can hold 2 electrons for a total of 6 electrons. And then in the third energy level, we're almost out of electrons. There's only one left. So that single electron is occupying the third energy level, and that third energy level is an s orbital. So here's the electron configuration for hydrogen. Here it is for helium. And then the bigger the atom, the more complicated the configuration of the orbitals are. Now, if you take higher levels of chemistry, then you're going to have to memorize the electron configurations. There's some tricks to do it. And in the past, we used to have you memorize configurations for this level of chemistry. We're no longer going to have you memorize the configurations for this one. So we'll cross that out. I'll probably erase it on your own personal slide copies. What you will have to do, I need you to be able to sketch an s and p orbital. I also need you to memorize the concept of orbitals, and then I could test you on general theory of orbitals. So theory, definition, and then sketch the S and P. As far as actually predicting or how to sketch the Heisenberg model, like we did the Bohr model, or doing the electron configuration, I am not going to test you on that. Alright, so we'll cross that out. We'll move on. We already talked about valence electrons. There was the outermost electrons, and they match up with the group number. So magnesium is in group 2, or 2A, and it has 2 valence electrons. Now, because it's the valence electrons that determine what type of reactions occur, we tend to focus on those the most and ignore the core. So rather than for magnesium, rather than drawing the complete Bohr model, oops, and I might even have too much. My bad. Let's pull out the periodic table and do that one over again, because I think it's on the 3rd energy level. Yep, it is. So then it would look like this. Awkward. Rather than drawing out the entire Bohr model as I just did, as I was time consuming and made mistakes, we're just going to focus on the outermost, aka valence electrons. And you'll notice that there is 2 valence electrons. Now, it's important that you go ahead and you label the electrons. I got a little bit lazy when I did this, but for each of the energy levels, make sure to populate 1 electron per 90-degree angle until you reach 5, and then you can keep populating afterwards. So why is that important? Well, you'll notice, and I'll just highlight this here, you'll notice for the valence electrons for the magnesium that I'm highlighting right here, the electrons are at a 90-degree angle to each other. What we're now going to do is we're going to do a shortcut, and I'm going to draw magnesium like this, where the dots represent electrons as well as the position of them, and there needs to be a 90-degree angle. So we call this the electron dot symbol. Electron dot symbol. There are 2 names for the same thing in chemistry. The other name is Lewis symbol. So for calcium, its outermost electrons look like this. Its valence electrons look like this. And so I'd go ahead and I'd draw the electron dot symbol like this. Now, we have multiple ways of drawing the electron dot symbol. As long as it's a not closer than 90-degree angle, we can go ahead and draw it, the electron dot symbol like this, where it's greater than 90 degrees. This is 180. We can also adjust the position. All of these are considered proper electron dot symbols. What you can't do is this right here. Now the only exception to this is helium. Helium, because it's the only one with a lone pair in the 1st energy level, then you can keep the electrons close to each other. So my advice is to look at the group number, and that tells you the number of valence electrons. So for example, for phosphorus, It's in group 5. So go ahead and use the clockwise method and populate the electrons like you did in the Bohr model. 1, 2, 3, 4, and 5. And you don't have to worry about messing up on the pairs versus unpaired electrons. So now I'll start using the term unpaired electron because there's no pairs versus paired electrons. The other way to draw it is like this. The bottom line is they need to be 90-degree apart from each other, and you need to have the proper number of pairs. So the one I did right here on the right is actually incorrect. This one would be correct because there's 1 pair and there's 3 unpaired electrons. Here's another version which is also correct. Again, 1 pair and then 3 unpaired electrons. So you have a little bit of leeway of doing it. I'd advise just sticking with the clockwise method because you won't make mistakes. 55 summarizes the electron dot symbols that I will test you on. Again, match up the group number, and that tells you the number of valence electrons, and then go ahead and use the clockwise method to put them in. Helium is the exception. And I'll be testing you up into period 1, 2, 3, 4. So let's investigate periodic trends. I'm going to go ahead and draw my periodic table right here. Looks like that. You can automatically assume that there is a trend that when you go left down diagonally, the bigger the element. So left down diagonally, the bigger the element. So just kind of memorize that trend. So this is just part of a periodic table. And I just wanted to show you that as you go left and down diagonally, the bigger the element. Now, they use the term atom, which is fine, element atom. So rubidium atom is bigger than helium atom, or rubidium element is bigger than helium element. They also use the term atomic radius. So that's the radius from the center of the electron to the outermost valence electron. But in short, the bigger the atomic radius, the bigger the atom sizes. So you're responsible for memorizing the trend. So that's just another reason why we organize the periodic table. Not only grouping exhibits properties, but there's also trends that are present. So memorize that trend. Your next question is why? Well, I'm not testing you on why. I'll give you some insight, but you're not being tested on why. One insight is as you go further down, then there's more layers of electrons that are surrounding the atom, and the puffier it gets. So the puffier it gets for each layer of electrons. Another counterintuitive reason, as the farther you go to the right, then the more outer electrons there are compared to inner electrons. Turns out inner electrons create this electrostatic interference. So think of like radiostatic. And when the electrons interfere with the pole from the nucleus, then the electrons are able to come further out. But the more electrons in the outermost energy level, then it actually makes the nucleus tighter. Again, I'm not testing you on that concept, just on the trend. So here's a question that I could ask you, or questions I could ask you based on the trend. The next one is ionization energy. So this is the last topic. Ionization energy basically means the energy to rip off electrons. For example, um, let me just go ahead and pick on, let's see, I'll pick on lithium. There's my nucleus. There's the inner electrons, 2 electrons, and then there's an outer electron. Now, it turns out that it's possible to apply a whole bunch of energy to rip off that electron. It then leaves this over here. Where there is a lithium with a missing electron. Okay. Now, an ion refers to an atom with a charge. Now you know the definition of the term ion. So this lithium now has an atom with a charge. So why does it have a charge? We'll get into this the next slide packet. But in short, here is neutral lithium. Neutral lithium had, to start off with, 3 protons and 3 electrons. Lithium ion, however, has 3 protons and 2 electrons. So you'll notice that there's one more proton than electron. And because protons have a positive charge, the lithium now has a positive charge. Ergo, it's now a ion. So ions are atoms with a charge. So the energy required to rip off that electron to form an ion is an ionization energy. Now, just using electron dot symbols to demonstrate this, here's my sodium. And then here's the sodium ion with the ripped off electron. As you see, the same thing in the example right below it. Some atoms are easier to ionize than other atoms. For example, lithium, it's really easy to rip off that electron. To form an ion. Whereas fluorine, it's much harder to rip off that electron. Oops. I drew the electron dot symbol incorrectly. That's actually a positive charge, but let me redo fluorine because we don't usually see it like that. It is possible, instead of ripping off the electron, to put an electron on it, but we're just going to stick with ripping off the electron. So there's my original fluorine. I'm going to rip off an electron. Now it looks like this, with a positive charge. We never see positive fluorines because it's so hard to rip off that electron. Why is this? Well, nature loves 8 electrons. So the closer it is to 8, it's like telling a person the closer you are to being a millionaire. And so if people get more greedy, the closer they are to become a millionaire. Well, electrons get more greedy the closer they are to complete the 8 electrons. So it loves the octet rule. It'd rather grab an electron to become an ion rather than rip it off. But at this point, I'm just testing you on the trend. So here's the trend. The closer you are to helium, the higher the ionization energy. So the more to the right you go and the more you go up, then the higher the ionization energy. So for example, chromium has a higher ionization energy than scandium. Or cesium has a lower ionization energy compared to argon. Oxygen has less ionization energy than fluorine. Neon has more ionization energy than phosphorus. So make sure you have those two trends memorized. Ionization energy going this direction, and then going the opposite direction, opposite diagonally, that's going to be element size. So that concludes this slide packet.